Okay, doing the video now. Hello, my name is Braden Miller, and I would like to show you a few things before I divulge into my PowerPoint real quick. This is my physical notebook, which I did over the whole course of the experiment. I recorded down notes from before my experiment, during my experiment, after my experiment, all the things you would need to have a successful experimental notebook that would include sketches and notes on what I would need to do. With that aside, here's my online notebook, which goes through basically from start to finish on all my slides. Oops, sorry, all my slides into a nice way where I can organize them, which is what I'm going to be going over with you guys. And it goes all the way to my abstract, which is the end of my experiment. So, let's start with my PowerPoint. My name's Braden Miller. I think I already told you that. But I'm doing a PowerPoint on wing airflow designs versus their climb, stall, and recover characteristics. My topic problem is if the KF wing design alters, then will that cause the flight characteristics and stall recovery to increase, decrease, or have no change? I'm going to summarize my hypothesis slide is if I change the KF wing designs and oppose the sort of normal airfoils that are used today, then there will be less drag and more lift on the plane. My null hypothesis is that if I change the KF step in design, then there will be no change to the flight characteristics of the plane. And my alternate hypothesis is if I can't change the KF wing designs, then there will be a quantitative increase in the performance of the planes. My rationale. Before my experiment, I did a lot of research into this subject, and I noticed that a lot of planes are still using outdated airfoils that definitely need adjusting. Obviously, not all planes are using this. A lot of commercial planes, pretty much all of them now, are using modern airfoils that do have good lift-to-drag ratios. But I would like to go into a different part of research and research different kind of airfoils that could potentially have better lift-to-drag characteristics and improve flight times, fuel consumption, and other things along planes. My outcome variable that will be measured quantitatively is the flight characteristics such as launch speed, apogee of the plane, and time it takes from the stall to the ground. I'll be measuring this in seconds in the air, distance from the ground, and feet per second. I'll use a digital force sensor, a camera, and other means of recording, such as a speedometer. Test variables are going to be the different 5 KF airfoil designs that I'll be using. I changed them by their position of the step and not their angle, actually. I'll discuss that later. And their depth of the step. I changed them this way because it would provide the most different results between each airfoil and would definitely be better or provide more different results than opposed to changing the step in other ways such as their width. My control group I used is the NACA 2414 modern airfoil. It's used on a lot of commercial airliners and definitely provides a baseline comparison to compare these KF airfoils to. My controlled variables were the fuselage, the design and shape of the wind tunnel, my measuring devices, my materials the wings are built out of, how the wings attach to the fuselage, not the software, the time spent in the wind tunnel, and the way the planes launch. My materials for the experiment are as follows. I used a lot of building material equipment such as cardboard, plexiglass, normal wood planks. I used paper for my consumable supplies. A lot of measurement devices such as a digital force sensor, not the software again, and measuring sticks. And safety equipment, there was none since it's not a hazardous experiment. I'm not going to directly go through all my procedures and read them word for word since that would be very boring for you judges, but I am going to try to summarize them in my best words possible. I, at the start of my experiment, had to build a wind tunnel. This wind tunnel consisted of an intake cone, a test section, a laminar section, a fan, and an exhaust cone. All 5 put together, as you can actually see in this background. all 5 put together into a nice wind tunnel. And there's a base. This wind tunnel uses different, you could call them angle steps that place the airfoils, which were 4 inches wide by 7 inches long, onto them, which I had to also create, and put them on them at different varying angles of attack to see how they would perform when going up to stall, their stall zone, which is pretty much close to 25-30 degrees. I then had to build a slingshot, which was relatively easy. I used a simple slingshot off Amazon and attached it to a few wooden planks to make sure that the plane could be pulled back to the same position each time. Basically, for analyzing my results from the slingshot and my wind tunnel, the wind tunnel was done in a weird way. I had to use a, I think it's called double-blind study to compare each airfoils to each other at different angles of attack and see which 3 out of the 5, or basically 2 out of the 4, since we were guaranteed going to use the control group, were the best, and move on to the flight. Then I used those 3 airfoils and attached them to the same fuselage each time using rubber bands, and shot them on my slingshot, and uses a video recording software to analyze each of them and track them to be put into graphs to be analyzed quantitatively later. I also was supposed to only do 16 trials, but I decided to put in the extra 6 hours of work to do 32 trials to have better statistical analysis and definitely better results in the long run. This is my data for launch speed. So as you can see, this is the control group. These are the 2 KF designs I'm using. I'll call this one KF1 and I'll call this one KF2 for ease of saying. These are all the trials up to trial 32. You can read over them if you want. I'm not going to. This is the data in Apogee, the second out of the 3 dependent variables that were tested, or not tested, were looked for. And this is the data in the 3rd dependent variable, time it took from the stall to the ground, and all my airfoils. This is the data summary, their mean for launch speed, the data summary for their apogee in flight height in feet. Launch speed is also in feet per second. This is their data summary for time it took from stall to ground in seconds. And I know I was kind of racing through that, but I'll definitely spend more time on data outliers analysis and statistical analysis. Data outlier analysis. I analyzed each of the 3 dependent variables, so one at a time, and found that throughout the whole thing there were no outliers. These numbers showed me if there was outliers, they would be under or over these numbers. So for launch speed there was no outliers, for apogee there were no outliers, and for time it takes from the stall point to the ground, there were no outliers. The statistical analysis, and this is where I actually have to get out, and because these green bars are not here for some reason, I don't know why. Statistical analysis for the launch speed showed that NACA 2414 and KF1 were statistically the same, with a 47% chance of, if you did more trials, they would turn out to be basically the same stats. The control group compared to KF2 was with a 7.5% chance, statistically the same, and KF1 compared to KF2 was different with a 0.9% chance of being the same. If it's over a 5% chance, you accept the null hypothesis that they have no change, and if it's under 0.05 or 5%, then you reject the null hypothesis, which is what you're going for, and accept the alternate hypothesis. This is also called a t-test, an independent 2-sample, 2-tailed t-test to be specific. In Apogee, it was a little bit different. The control group compared to KF1 was statistically the same again, but the control group compared to KF2 was statistically different, and the KF1 compared to KF2 was statistically different. The same for time it took from the stall to ground as the last time. Control group compared to KF1 was statistically the same. Control group compared to KF2, compared to KF2 was statistically different, and KF1 compared to KF2 was statistically different. And this is the time it took from the stall point to the ground. These are my graphs detailing all my 32 trials and their different airfoil designs. So this is launch speed, this is apogee, this is the time it takes from the stall point to the ground. Alright, from current slide. Data interpretation. NECA was expected to perform relatively well since it's used on a lot of modern day airfoils, and it did in a pretty decent way. The null hypothesis, if I change the KF wing step in design, there will be no change in the flight stall and recovery point of the plane, was partially accepted and partially rejected. As I went over in my statistical analysis, most of them, I think, yeah, on the launch speed, 2 out of the 3 were accepted the null hypothesis. On the apogee, 1 of the 3 accepted the null, and on the time it takes from the stall point to the ground, 1 out of the 3 accepted the null. P-values occurred between these. I'm not going to read them off. That would be boring. My claim. So, the larger low-pressure air pocket on the KF airfoil 1, which is short length, long depth, is statistically the same as the control group, but it did show slightly better results. I can't make a claim off this, but it did show better results, but statistically they weren't actually better and they were the same. KF1 compared to KF2 was statistically different and definitely better. Same goes for NACA 1 compared to KF2. Statistically different and NACA was definitely better. Justification. The scientific principle of Bernoulli's law, I think I said that right, although correct me if I'm wrong, states that the lower the pressure over an airfoil, there will be more lift. This is what all bases of airfoils are dependent on, and the reason why NACA has definitely good stall or flight stall and recovery characteristics. This is also why I think that the short depth or short length, long depth had a more lower pressure air pocket and thus allowed for better low pressure circulation of the airfoil and lead to better stats than the other ones. Obviously, if you want to, make sure to pause and read over all my slides, as they're definitely helpful if you read into the details of what I did. This scientific project does support most current research online, as most current research explains that KF airfoils perform better at lower Reynolds numbers, which means at lower speeds, basically, because Reynolds number is how fast wind is moving over an airfoil. And if I definitely lowered the speed of this thing and made a lighter, more, I would say, like, made out of balsa wood or something like that, I would think that the KF2 design would perform better, or at least the same as the control group airfoil and KF number 1. This is my bibliography on all my research, where I got to learn how Reynolds numbers, I got to learn how to make a wind tunnel, I got to learn how to make airfoils, and I got to learn how to all laminar and turbulent airfoil and all the good stuff of performing, you know, a science experiment and what it could allow me to learn. I really can't go into the specifics of what I learned, since this was actually in October, I believe, but credits, all my data tables and graphs were created by me, the researcher. All photographs, which I'll go into next, were taken by either me or my parents, which were supervising me during this project. These are my photos. Number 1, starting points outside, first wind tunnels. This is the short length, long depth airfoil that actually performed the best, or very similar to this control group airfoil that I made. And these were the longer ones that were used on the real slingshot testing. This is all my airfoils complete, my wind tunnel design, exhaust cone, intake cone, laminar section started, test section that I built, my fuselage, laminar section, my base, my finished wind tunnel, voila, my finished slingshot. This is how I used a little nail and pulled it back, my angle of attack for my slingshot, and my airfoils compared to each other. Thank you for listening to my science experiment. I hope you have a wonderful morning, evening, night, wherever you are. Thanks a lot.